I'm going to talk about something kind of similar. It's also going to be opinion dynamics on networks, but here it's going to be, you know the network, but you're trying to change the network. The idea, if you think back to when social media actually used to contain posts from people you know about the things that they were doing with their lives, maybe you have one friend who likes to post pictures of cats a lot, not necessarily their own cats, just sort of any cats that they come across. And it still happens that whoever owns this social media site is also a big fan of cats and thinks that everyone else should also be a big fan of cats. So gradually just start sort of sneaking in a few extra posts from that friend of yours who really likes to post pictures of cats. They're not creating any new content themselves, so they're not directly influencing your opinion, but they're influencing instead the amount that you see content from other people. So this is the idea to keep in mind. So I'm going to leave a cat in the corner throughout most of it. The model we'll actually use is an ODE model for opinions. Apologies to those of you who have been to my talks before and probably recognize bits of this. We have each agent has an opinion xi. It's going to be a continuous opinion somewhere between -1 and 1. And their ODE for their opinion is going to depend on sort of averaging over their interactions with everyone else. So for each person, J, they look at the difference between their opinion and your opinion to know what direction your opinion should move in. And then that's weighted by this interaction function that says, based on the difference between your opinions, how much do you listen to what they have to say? So for example, the one we're going to talk about mostly is this red one here, where you have some cutoff point. And if you're within that opinion, if your distance is smaller than that cutoff, then you listen to the person. And if their opinion is further away than that cutoff, then you ignore them. The idea being that if people say things that are just sort of too extreme, you basically just don't, you just don't listen to them. Or you could have the green one is basically the same thing, but a slightly smooth version so that it's continuous. But it still is 1 below some value and 0 above some value. Or you could have something like an exponential one. So as somebody's opinion is further away from yours, you just gradually listen to them less and less. You're also going to weight people's opinions by a network. So this Wij is the weight of the edge between person I and J. So this could represent sort of physically how much you see a person. So like the people in your office, you might have a very high weight with. The people in your department, you would have a slightly lower weight with. And then people sort of that you don't know, you would have no weight with. It could also represent maybe like how much you trust a person, or in the social media example, how much you see content from a particular person. So you could just have a binary 0 or 1 for if you follow people, or it might be weighted according to how frequently you see their posts, so how many cats you're seeing. And you're dividing by this ki, which is the sum of the weights, or sort of the total number of posts that you're seeing. I didn't forget about cat. Yeah, so this first two is basically your opinion dynamics running without any control. So does this bit make sense? Yeah, cool. The thing that we're adding is an ODE for each of these edge weights. And this is the thing that we're going to control. These Uijs are the controls. So they're a value between -1 and 1. And they're going to describe how we change this edge weight. So if the control is 0, nothing's going to happen. If the control is 1, we're going to create an edge between two people or strengthen an edge. And if the control is -1, we're going to get rid of an edge. It depends on these functions S and L. So S is the speed of the controls and L is the direction. For example, your speed might be quadratic in the size of the control. So if there's no control, there is no speed and nothing happens. And then as you make the control stronger, it starts to act faster. And at the same time, this target is affecting where you're moving the edge to. So the structure of this ODE is that the weight Wij will move towards whatever this target is, and then this function will control the speed at which that happens. The goal is to pick the controls as functions of time, so that you bring the population to consensus, so everyone agrees, and they agree at a value that you have picked. So some examples. This is time on the x-axis and opinions between -1 and 1. The coloured lines are people's opinions over time, and they're coloured according to their starting opinion. And this dashed black line is the target. So for example, we're guiding everyone to 0.5 or minus 0.2. These are just two sort of examples of possible controls that work. Your controls that you apply don't have to be continuous. So you can switch your controls directly between plus or minus 1. So you can have a weight. You can change the edge weight so it's sort of going up and down or going straight up to 1 and staying there. The weights will move continuously because it's an ODE, but your controls don't have to be continuous. Okay. Questions. If we have the initial opinions and a target, is there a control that will get us to consensus at that target? Is basically the big question. If the control exists, how do we actually find it? If we can find it, is it actually any good? We would need to define any good properly. But basically, you would maybe you want to get people to consensus at that target as quickly as possible, or you want to do it applying the minimum amount of control possible, or you want to do it only affecting the smallest number of edges or something like that. And the last question is, if we can't find a control, how close can we get? So maybe our target is really high at like 0.9, and we can't actually get everyone to have an opinion that's that high, but maybe we can get everyone to 0.7 or 0.8. I'm just going to talk about the first one because they're quite difficult. Yes, so what I mentioned about it not being continuous, but it turns out that most of the time you want to apply the maximum control. So either you have your Uij, for a Uij, so the control for the weight Wij being 0, so you're doing nothing, or it's 1, and you're exponentially increasing the weight up towards 1, or it's minus 1, and you're exponentially decreasing the weight down towards 0. I'm going to restrict it to these just because it makes things a lot easier, and those are the ones that it turns out to basically always use anyway. So, when does a control exist? There's basically only two things that can go wrong. The first one is that your opinions split into multiple groups. So if we think about a bounded confidence interaction function where it's cutting off after some point, you'll only interact if you're within some distance. If your population splits into two groups that are a distance apart that's too big, they'll stop interacting with each other. So it doesn't matter what you do to the weights, so people aren't going to listen to each other. So you've basically failed. The other thing that can go wrong is that everyone ends up either above or below the target. So you're not influencing people's opinions directly. So you can't push this group up. You can only show people more or less of opinions that currently exist. So if everyone is above or below, then you've failed again. Fortunately, these are the only two things that can go wrong. If you can bring everyone to consensus and you can keep that target inside the opinions, then you're fine. Then you'll get consensus at that target. So we'll assume that at the beginning, the opinions aren't clustered, that they're relatively evenly spread, and that they contain the target opinion. So we're in an okay starting position. Unfortunately, for any target, there exists initial conditions that satisfy these assumptions where control is not possible. These are relatively straightforward to design. If you imagine that you pick some target X star, and then you design an initial condition where one person is just below it and everyone else is sort of a bit above it. And they're close enough together to still be inside the bounded confidence interaction radius. So they could still interact, but you create really strong edges from this person to all these people over here. Because the speed of the controls is bounded, if you put this person close enough to the target, they will sort of almost immediately cross over the target before the control has enough time to prevent them. So you will fail to control 2x star because everyone will be above it. So this question that I put up is kind of the wrong question. A better question is that if instead we fix the initial conditions, what targets can we reach? And this is the one that I will try and give an answer to. This lemma is going to be really, really useful. Basically, if we pick a person, person I, and we set all of their controls to -1, so we're decreasing their edge weights with everyone. They'll always listen to themselves with weight 1. We can't stop people having sort of self-confidence. But basically, we remove all of their edges to everyone else. So they're not listening to anyone else. We basically just show them nothing on their social media. How far could their opinion change? So if you imagine that they start off connected to lots of other people, we start decreasing those edge weights, they're still going to move towards those people because they're still connected to them a bit, but the edge weight is getting exponentially smaller. Basically, that means that it's an exponentially decreasing towards zero, so it's never going to reach zero, but it will become very, very small. So basically, the amount that you actually move using that edge is limited. So if we return to this sort of bad scenario before, if all of these edges here, we decrease them all as quickly as possible, we can basically bound how far this person can possibly move. So if our target that we're aiming for is somewhere in this region here, basically it's above this bound, then this person here, we can make sure that they always stay below it. Yeah?
So is that something you've imposed on the controls, is you can't set it to zero, you can just make it exponentially small?
Basically, because the weights are following ODEs, if it starts non-zero, it will exponentially decrease towards it, but it will never actually reach zero.
Okay. So, but the controls, you can't just...
You can set the controls to -1.
So if you set the controls to don't see anything else, they'll still drift in the direction they've already got momentum, is that what you're saying?
Yes, if you set all the controls to zero, you're leaving the edge weights at their current state.
Yeah.
So people will continue to move wherever they would move.
Oh, okay. Sorry. So you can't. You're not influencing the edge weights directly. You're just influencing.
You're influencing like the dynamics of the edge weights.
Okay,
so you're decreasing the weight to them or increasing the weight to them or doing nothing.
Okay.
You're not fixing the edge weights immediately. So yeah, we can, if we set all of the person's controls to -1, their edge weights with everyone will start to decrease, and we can bound how far they'll move. I'm going to assume that the interaction function is just 1 to make it a bit easier. So people will always interact. That stops the problem of clustering. We'll always get consensus as long as the network remains kind of connected. So this gives us a bound, a region of targets where we can guarantee controllability. And basically, we're applying this lemma to the person with the minimum opinion and the person with the maximum opinion. So we take our person with the smallest opinion over here, and we work out the bound on if we remove their edges to everyone, what's the maximum that they could possibly go. And we do the same for the person at the top here. And we basically want that our target opinion is somewhere between this upper bound and this lower bound. So we sort of trap these end people to start off with. And then for everyone else, we connect them to the other end person. So all the people above the target, this is our target here in the middle, all the people above the target, we connect them to this person over here, and all the people below the target, we connect them to the maximum opinion. This is basically going to bring all of these people towards the target and all of these people towards the target. So we're sort of gathering all the middle people closer into the middle. Also, this basically means that now we only have to worry about controlling the end people. Because if we can control the end people, then everyone else is attached to one of the two end people. So basically, once everyone else is sort of gathered in towards the middle, we connect each of the end people to each other. And this will sort of close this end distance. So the people at the end are basically only listening to each other, and the people in the middle are only listening to the people at the end. Yeah, and we've made it so that the people at the end will always stay on the right side of the target. So basically this picture is just going to sort of shrink down around the target. Something that I think is kind of cool about this is that you need the intermediate value theorem to show that the control exists. Basically, you're going to create an edge between these two people, one edge in that direction and one edge in that direction. And you're going to turn the controls on for a bit, until the edge weight reaches some number, and then you're just going to leave at that number. And you'll do that for both of them, and that will control the speed with which they both come in. So if you give them both the same edge weight, if you make these edge weights the same, then they'll come in with equal speed, and they'll meet basically in the middle, which is, in this case, slightly too far to the left. If you make this weight this edge here slightly stronger, then this person will move slightly faster and they will meet slightly further to the right. And basically you can show that if you time the controls properly, you can get the perfect balance between these two edge weights so that your end people meet exactly where you want them to. And then everyone else is just attached to one of the end people. But yeah, you need to show that the location that they meet is continuous with respect to the controls, and then you can show that a control exists that achieves what you want. You then have to do some numerical work to actually find a control by testing out values and sort of repeatedly improving them. And you probably can't find a control that gets you to exactly the right point, but you can find one that gets you within whatever accuracy you like. Because you're using the intermediate value theorem to show that it exists, not to actually find what it is. Yeah, when we want to control the system, the two main things we have to worry about is stopping the population splitting up into different groups to make sure that we get consensus, and then keeping the opinion inside the current range of, keeping the target inside the current range of opinions. We can use sort of a worst case scenario to come up with bad counterexamples, but also bounds on how far people could possibly move. So that lemma that was useful, you can basically, you prove that by thinking the sort of worst case scenario, how far could they possibly go? And then in the simplified case, this gives us an explicit region in which we can guarantee controllability for any starting network. If we assume specific network structures, then we can prove things that are a bit more specific. So that's kind of a bit of an answer to the first question. For the second question, when it comes to finding it, the proof that I described just now gives you one method for finding a control, but it's not a very good control. You have to basically remove a lot of the initial edges that you probably don't need to. So the other thing we looked at in the paper was optimal control, which I'm not going to talk about today, but will feature in my poster at the retreat. And then this last bit about if we can't find a control, how close can we get? I have absolutely no idea. So yeah, thank you. I'd like to thank my supervisors, Susanna and Marie-Therese. This is a QR code for a paper that we've just put on archive that describes this and the optimal control stuff and one other type of control called instantaneous control and looks at how well each of them work for this problem. Thank you very much.